Hello, and welcome to my interview with climate scientist David Archer. I'm your host, Dan Miller. David Archer is a professor at the Department of Geophysical Sciences at the University of Chicago. He has worked on a wide range of topics pertaining to the global carbon cycle and its relationship to climate. In our interview today, we are going to discuss David's recent research on the ultimate cost of carbon. In other words, what is the cost to society of emitting a ton of carbon today if the future negative impacts are not discounted, as is done in most such analyses. We're also going to talk about CO2's very, very long-lasting impacts on climate once it is emitted. This interview is part of a series of interviews with climate scientists, technologists, authors, advocates, communicators, and others involved in understanding and fighting climate change. It is sponsored by the Climate Chat Club on the social platform Clubhouse. If you are a member of Clubhouse, please join our club. And now, my interview with David Archer. I want to welcome David Archer to the stage. And David is a researcher at the University of Chicago, and he wrote a very interesting paper about what the ultimate cost of carbon is, and we're going to be talking about that. But David, before we get started on that, can you please give us a little bit of your background and how you came to the University of Chicago and this project in particular?
Yeah, sure. Well, I'm not an economist. I've never written a paper before that had anything to do with money, and I don't really expect to. Again, I'm a carbon cycle modeler and interested in how, among other things, in how the natural world will clean up the fossil fuel CO2. And the astonishing thing about that is how incredibly long that will take. I didn't discover that. That was discovered. It was like figure number 27 on in a paper where they put CO2 into the atmosphere of a model and noticed that it didn't ever go back down all the way to the original value. So it's not like, and since then it has sort of held up scientifically. There's no real doubt about it, but it's a hard thing for people to kind of psychologically wrap our heads around. Deep time in general is just crazy hard to think about if you haven't sort of tried and trained and meditated on it. And deep time into the future is even harder. So the deal with the carbon cycle is that when you dig carbon out of the earth and put it into the atmosphere, it spreads out around in what we call the fast carbon cycle, which is the oceans and the land surface. But the whole fast carbon cycle stays kind of fat on excess CO2 until there's this sort of planetary thermostat mechanism that operates to sort of regulate the CO2 concentration in the atmosphere and Earth's temperature. And it's kind of why the Earth's climate has been as stable as it has been through Earth history. But the bummer is that the time scale for that sort of Gaia cleanup process is hundreds of thousands of years, maybe 500,000 years or something like that. So I've spent a fair bit of time trying to, raise awareness about this, because it kind of changes, the picture for me. If it was going to go away in 100 years, I would be far less bothered by, filling up a car with gas and all of that. Nuclear waste is supposed to last for 10,000 years, and the repository for that is supposed to plan for that. And if it turned out it was only going to last for 100 years, that would make a big difference to, the planning of that waste site, and also, my personal feelings about nuclear energy. So the long time scale matters to me anyway, but everybody misses it. I read a great book recently by Oliver Morton on geo-engineering called The Planet Remade. And, this is a very smart guy, and it's a great book, but he gets it wrong. Elizabeth Colbert in Field Notes from a Catastrophe got it wrong. Everybody gets it wrong. Scientists get it wrong who aren't working on the carbon cycle. So this paper was, trying to make a point about how long the impacts last. Okay. So I had to make a few wacko assumptions to add up a number over that amount of time. But the economic treatment of climate change is sort of chopped off by the practice of discounting, where costs in the future, say 100 years from now, they don't really matter to us today because we could invest a couple bucks in a bank account theoretically, and it would grow, to $100 in 100 years or something. So $100 in 100 years shrinks to a couple dollars today, and costs 1,000 years from now, don't amount to anything to today. So people like Nordhaus and Bjorn Lomborg are calculating, the optimal amount of CO2 to emit based on this incredibly short-sighted measure, the social cost of carbon. So
Right.
I just wanted to add up the numbers of what it would cost if we didn't discount, just to make a point about how myopic that whole analysis is.
Yeah, and I think that comes through in your paper, and we're going to definitely talk about that. But let's come to start out with the conclusion of the paper. What number did you come up with for the ultimate cost of carbon?
Something a median sort of best estimate was like $100,000 per ton of carbon,
Mm-hmm.
and you can compare that to about $100 per ton of carbon for the present day value of the social cost of carbon. So it's a much bigger number, many orders of magnitude bigger.
And I think one thing that we have to be clear about is 100. You're talking about tons of carbon, and for every ton of carbon emitted, it takes on two oxygen atoms and becomes heavier.
Right,
So CO2, I think, weighs 3.7 times as much as an atom of carbon. And so if we
right,
translate that $100,000 of per ton of carbon, we end up with $100,000 per ton. I'm sorry, $27,000 per ton of CO2. Is that correct?
right. I think that's right. Yeah, it's endlessly confusing. Chemists don't like to do things in mass units because you have this kind of problem. If we were counting molecules and talking about moles of carbon, then this wouldn't be an issue.
Right, but
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 it's
sometimes
endlessly
people talk
confusing.
about when you talk about carbon capture, for example, usually the price is dollars per ton of CO2. It's
Yeah,
almost
and when you
always
talk about carbon release, it's gigatons of carbon released. So it's
right. Well,
endlessly
sometimes it's
confusing.
CO2 also, right? I mean, I see it both
Yeah.
ways.
Yes.
For everyone in the audience, just keep that in mind that you have to be very careful when people are talking about gigatons of C or gigatons of CO2. And again, they're the same
Right.
thing, except it's just a different unit. And CO2 weighs 3.7 times as much. So the cost per ton is 3.7 times less. So, okay, so we have those numbers. Those are still, whether it's CO2 or C, it's still a really, really big number compared to $100 a
Right.
ton. Uh, so that's much lower. Um, so tell us what's the difference? So you talked about it a little bit, but maybe you can explain a little more what the difference between the social cost of carbon is and the ultimate cost of carbon.
Yeah, they're apples and oranges. They're not comparable, and the fact that my number is so much higher than the social cost of carbon doesn't mean that I'm attacking the social cost of carbon, directly per se, because they're very, very different. The way the social cost of carbon is predicted is by taking a nominally realistic model of the economy today, which is undergoing exponential growth, and then trying to project that forward with and without uh, some assumed impact of climate damages, and also maybe the expense of mitigating or preventing CO2 release, and then uh, they discount that to get the present day value. So to predict the future of human activity for 500,000 years is obviously nuts and something that I couldn't deal with. So the ultimate cost has to be a lot simpler in formulation in order to just be tractable at all. So we can't have the answer that we might, most want, but we can have this sort of idealized answer, which is um, based on kind of magical assumptions of uh, human population in uh, steady state with the carrying capacity of the planet. So the modeling people kind of the way a natural scientist might model, mosquito populations or something. If you have more land that is good conditions for mosquitoes, you might have a bigger population of mosquitoes. If you have sea level rise that gets rid of the agricultural capacity for humans in the steady state in my model, you would have fewer humans. So um, the 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 review process. I didn't have any economists as authors of the paper, although I tried. But I had economist reviewers for the journal, and the whole process was about trying to figure out what kind of magical circumstances my number would actually, be strictly correct in. And it turned out to be kind of nice. It would be correct if today, this afternoon, and everybody, in the world were going to persist just like this forever. What would it cost us if we were going to live forever and there was not going to be any more economic growth? They're just taking a snapshot of today and extruding it into the indefinite future. And it's not realistic. It can't be, but it does have the virtue of being sort of easier to visualize as kind of a scale bar for how much of a bother this whole thing will cost over its entire duration. So
Well,
one thing that I
well, it
put
gets
into
future
it was,
generations, and the social cost of carbon is what is the cost to us if we screw all our future generations and we don't care about them. But I think when
yes,
you don't discount, you basically take into account all future generations. It's one way to think about
yeah,
it.
that's right. That's the way I initially conceived of it, is sort of a cost that's distributed in time instead of, the present day value, which is what the social cost of carbon is. But the uh, the economists who were, looking this thing over kind of insisted that it had to be like a present day value of some sort, and what would that take? They didn't buy the cost distributed over time line. They wanted to make it a present day value and figure out what world that would be the right, answer in.
Okay. Well, we're going to get into that. But I think it's really one of the fascinating parts of the study, and also what your other work is on, is about this long time frame. So I think that's really cool, and we're going to talk about that. But let's keep going a little bit on the actual paper and the model. So more on that. Like, so the time scale for social cost of carbon is like the next 100 years, but heavily discounted. So really, just in the next you know. 20
Yeah,
50 years really the
yeah,
costs kick in, and your model is
right.
the next 500,000 years, is that correct?
Yep. Uh, that's basically how long it takes for this planetary thermostat to clean up the CO2 that we release. So climate is also changing naturally, and I can't really include that very well. So what I'm modeling is a sort of perturbation that starts today and kind of slowly relaxes back to zero. And yeah, I had to go out like a 500,000 years to really make that go away.
So another way of looking at it, when we put out a ton of CO2, it has an impact on the earth that's longer than the time since the current species of humans have walked the earth, which I understand is like a few
I
hundred
guess
thousand
that's
years.
true. I mean, maybe anatomically modern humans go back a couple million years, but
Right,
agriculture only goes back 10,000 years,
right,
and creative, social humans who had like culture go back maybe 40,000 years.
right.
So, yeah, this is a really unimaginable length of time into the
Wow.
to the future.
Okay. So tell us a little bit about the model and what your major assumptions were in the model. So you said you had to simplify things in order to do it. So what were some of those major assumptions?
Well, it starts out with a slug of CO2 that's added to the fast carbon cycle. Um, in reality, it takes some time to for CO2 to when we release it to the atmosphere, it takes hundreds, maybe 1,000 years to dissolve in the oceans. And that transient, that initial, spike of CO2 in the air, I kind of toss that out. So I start time zero when the carbon is equilibrated with the oceans and the land biosphere, but it's higher than it was in the natural system. Um, then over time of about 10,000 years, although this is one of the model parameters that is a variable that tests the impact of the pH of the ocean gets restored back toward its original value. There's a pH thermostat kind of a mechanism in the ocean involving the dissolving and burial of calcium carbonate, which is like an antacid. So the ocean will get somewhat more acidic because of the fossil fuel CO2, and then on 10,000 year time scale, it will kind of get restored, and that'll allow the ocean to take up somewhat more of the fossil fuel CO2. But then you've got to wait for this planetary CO2 thermostat to make the CO2 go away the rest of the way. And then there's so the temperature is predicted just using a climate sensitivity of 3 degrees centigrade, although that's another model parameter that turned out to be the most important one in terms on the geophysical side, is what the value of the climate sensitivity is, how much warming you get for doubling the CO2. And then sea level has a kind of a correlation with global temperature going back through time that I relied on going forward. And ice sheet models do this as well. It takes ice sheets thousands of years, a few thousand years, to equilibrate to the temperature. I mean, we hope it takes that long. There were ice sheet purge events called Heinrich events during the last glacial time that were more like 100 years and maybe 10 meters of sea level rise. So I'm skeptical that it's really going to take that long, but I was trying to be conservative throughout, doing this. So 3 degrees C is about enough to, in the steady state, which takes maybe thousands of years, enough to melt the ice sheets pretty much completely. So we're talking about a maximum of like 70 meters of sea level rise.
280
So
feet.
then there are two different components of climate costs that I put in. One is sort of a direct climate, temperature cost, which is again conservatively based on the relationship between temperature and what the damages would be in some of these, like the DICE model of something like 1% of cut in the economic activity per degree C of warming, which we were talking earlier, and that seems absurdly low to both of us. But I wanted to be conservative and not be guilty of pushing things too hard and jeopardizing the whole thing. I could get a pretty big number without pushing things too hard.
So that's
So
pretty important, by the way. So I'll repeat it and make sure I got it right. So you assumed the cost of climate change is equivalent to 1% of the global world production, or similar to GDP. 1% of that for each degree Celsius of warming caused by the carbon.
Yeah.
And just for reference, we had climate scientist Kevin Anderson on a couple weeks ago, and he's kind of famous for saying at 4 degrees warming, it's not compatible with an organized global community. So you could count that as being 100% damage at 4 degrees. So you are being very conservative when you use the 1% number.
Yes. So that's one component of the cost, and the other component is based again on treating humanity in steady state with the carrying capacity of the planet, which those phrases get me laughed out of the economics department here. But so the idea is that if by flooding 50 or 70 meters of sea level, we will sacrifice a lot of good farmland. And so there's a lot of good agricultural land in sort of low-lying river deltas that will get flooded. So, in a steady state, if you had a population of mosquitoes and you gave them 10% less food, you would expect to have 10% less mosquitoes in the steady state. So I put that in as another possible source of cost that, we could have like basically a smaller planet, a less carrying capacity in the future because we lose all the sea level. So there's also land that's, too cold today, and like northern Canada, or, under the Greenland ice sheet, or Antarctica or something. And it could be that, when you warm up the planet, could sort of move up there, and maybe, that could sort of ameliorate the damage. And how fast that could happen would depend on the rate of soil formation, which is maybe roughly sort of 10,000 years. That's the amazing thing about soils, is it takes so long for them to form. The Canadian Shield is crummy for agriculture today because the ice sheet scraped off the dirt, and it's just a Canadian Shield now, and the soils are thin, and it's been 10,000 years. So
That's, by the way, an important point that
that's
people don't realize is that, oh, don't worry, don't worry when, the United States turns to desert, in terms of the western side for growing food. We'll just move up to Canada and plant there. And they don't realize that, no, Canada dumped all its good soil on us in the last ice age, and
yeah,
and they don't
right.
have it up there. So just because it's warmer doesn't mean you can grow a lot of food. These are some of the
And one of the countries that stands to benefit from climate change is Russia. I'll just leave that scary statement hanging there.
Yeah, that's true. Yeah. So, wow. Okay, we're gonna. Yeah, that I think is one of the really interesting parts of what you've done. So I do want to spend more time on that. But let's. What are the major variables that you use? Like, temperature and sea level rise. What were the other major variables that
Well,
you were tracking?
those were variables that were, internal in the model. The parameters that go into the model. There was the amount of carbon that gets released determines what fraction stays in the atmosphere in the early stages, because the more we release, the more it, alters the chemistry of the ocean and depletes its buffer capacity. So if it's a bigger slug of carbon, 5,000 gigatons of carbon, as opposed to, say, 1,000, which is about what we've already sort of more dust done, then the atmospheric fraction goes up. There's a carbon cycle feedback factor reflecting the expectation that when it gets warmer in the high latitudes, there's all this organic carbon that's frozen in permafrost today that will melt and probably decompose, and that could, amplify the amount of carbon that we put in. There was a parameter, how long it takes for the ocean pH to recover, so that could be 1,000 or 10,000 years. Another parameter, which is the CO2 thermostat time, which we know is longer than 100,000 years because the glacial interglacial cycles modulated the CO2 up and down, and the thermostat wasn't able to keep up with that. So it had to have been longer than that. And 200,000 years is kind of a best guess. There's parameter, how long it takes for the temperature to come to equilibrium with the CO2, because the ocean is a big heat sink, and today the oceans are keeping us cool. So the time scale for warming is something like 1,000 years, governed by the circulation time of the ocean. Another one is the time it takes for ice sheets to melt, and we talked about that already. It could be that we've triggered a lot of that to already happen. Maybe there's runaway stuff happening in the Pine Island Glacier and stuff, places like that in the West Antarctic ice sheet already. But I just treated it as linearly responsive to the temperature, and if we backed off on warming the temperature, we could back off on the sea level rise. So again, maybe conservative. And then finally, the climate sensitivity, how much warming you get from doubling CO2. So
Right.
that's like 7 parameters for
What did you assume for that, by the way?
geophysics.
3 degrees?
Say what?
What did you assume for the climate
Yeah,
sensitivity?
I assessed the sensitivity in the range from 1.5 to 4.5.
Oh, you did that. Okay. Okay.
And
By the way,
so,
let's get back to
turned
something
out,
you just said. I'm very interested,
yeah,
since you know about this stuff, and not too many people do. You said it takes a long time to settle on the temperature. So there's so much
yeah,
talk at the IPCC about 2 degrees and what budget we could meet for 2 degrees. And if we get to net zero by 2050, we can stay at 2 degrees or
yeah,
whatever. Let's say we meet some budget that keeps us at 2 degrees in some near-term time frame. What happens to the temperature as CO2 continues to do whatever it does over the longer time? Let's say the next 100 or 200 years. What happens to the temperature? Does it stay at 2 degrees or does it go up after that?
Well, it's a little complicated because so we say we put a big slug of CO2 in the atmosphere all at once. The CO2 is invading the ocean, and so it's going down from the atmosphere at the same time and on the same, governed by the same process as the temperature of the surface is rising. Both are governed by the overturning circulation of the ocean. So the way it sort of looks is if you look at a detailed model of this, there's a paper by Peter Clark that I could point to that has great graphics, shows model runs both in the near term and out to like 10,000 years. You get like a spike of the CO2 concentration, and then it kind of comes down fairly quickly over, centuries, somewhat, and the temperature is it kind of parallels that, but you don't have the big spike at the beginning so much. So you have the spike while you've got this transient of invading the ocean and warming the deep ocean, but you see it more in the CO2 than in the temperature. So the temperature kind of goes up, and then basically, it drifts down a little bit, but mostly it's just at the new normal. It kind of does go to a plateau fairly early, as I understand it, and then it just stays there. So the peak temperature formulation isn't horribly deceptive in that regard, I guess, if we really, stopped moving CO2 around and just let the thing equilibrate, from the year 2100 or something.
And back to something else you said about sea level rise. 70 meters or 280 feet of sea level rise is a lot of sea level rise. That would destroy essentially every single major coastal city. Well, every coastal city in the world, and every island nation would be basically destroyed.
Yeah.
But you don't actually account for that cost in your model. And can you please explain why?
Yeah, well, on timescales of thousands of years, it seems to me, cities need to be replaced and renewed anyway. So I figured if I, added up the cost of all the buildings in Miami and called that part of the cost of this on long timescales, it would get pushback. So I didn't try to account for that at all. I figured it would be negligible on the long timescales.
Which is kind of amazing to think about. In the short run, it obviously would be maybe the biggest cost of all. Well, one of the biggest costs, and yet in the long run, I agree. You would just build cities inland, and you'd have these new shorelines. Did you take a look at any what I would call game over scenarios, like a certain amount of CO2 leads to the collapse of civilization or human extinction or anything like that?
No, it's a hard thing to calculate the cost of.
Well,
this is all,
or it's easy depending how you look at it, right? It's 100%.
Yeah, I guess. Yeah. No, this is sort of like a best case scenario almost, in that there are no surprises, but only the things that we really kind of expect and know will happen. Interestingly, getting this paper was the hardest. Getting it published was the hardest paper I've ever had. It went through 4 rounds of review, and there was no pushback at all in any of the geophysics. It's just, the economics, not even the numbers, but just, what does the formulation kind of mean?
Okay. Well, okay. So you use this. So speaking of that, being conservative, you use 1% per degree C, and so on one hand, this model is very conservative in that it assumes not not much damage compared to what we could really see in the short run. But on the other hand, it has a very long time frame, so that people we're looking at costs going way into the future, where a lot of people today might not care if what happens 1,000 years from now, for example. Is that right?
Yeah. So, it's just my attempt to change the units from, years to dollars. Another way you can kind of do that is this is an idea that Ken Caldera came up with. You can add up how much energy you get from burning a gallon of gas and, call it joules of energy. And then you put that amount of CO2 in the atmosphere and let it stay there for hundreds of thousands of years. And it leads to a very, very tiny energy imbalance in watts per square meter, but you multiply by the surface area of the Earth to get rid of the square meters, and then by time to go from watts to joules. And it turns out that the unwanted greenhouse energy from that gallon of gas is about equivalent to the Hiroshima bomb. Just a massive, energy perturbation from just a tiny little gallon of gas. And the difference is, again, because of the immense amount of time that it operates in the atmosphere.
So that's very interesting. By the way, I'm the one who came up with that Hiroshima atomic bomb thing with Jim Hansen when he gave his TED talk, and the answer there was, the Earth is not in energy balance right now because there's more sunlight coming in than going, more heat coming in than going out, or energy coming in than going out because of the extra greenhouse gases, and that amount is equivalent to currently. Back then it was 400,000, but today about 500,000 Hiroshima atomic bombs going off every day. Which now you're talking, your Hiroshima atomic bomb is different. Yours is the entire over all time. Which is another way of looking at it.
So it's a very, very slow nuclear explosion.
Right. Which is still amazing. Right. And one other number I heard that's similar to that is that if you use a hair dryer for 1 minute while you're, drying your hair in the morning, that hair dryer was supplied with electricity that caused a little bit of CO2 to be released. And if you took all the heating from that CO2 over all time and compressed it down to 1 minute, it would be equivalent to a 747 airplanes taking off at full takeoff power. That would be the heat generated by your hair dryer, which is the same kind of thing. That. Like a gallon of gas is a Hiroshima bomb. By the way, that one I got to get my head around a little bit, because think of driving your car. What did you look in the rear view mirror and you see this cloud? This mushroom cloud. Yes, Stacy.
Right.
Go ahead.
Yes. Can you help the slow girl here? Because I want to understand this, because this seems like a very impactful statement.
Okay.
And as someone who has COVID has allowed me to try not drying my hair. So that was, that really caught my ear. So I'm not getting the gallon of gas, which, could be viewed as similar to the running your hair dryer. So can you break that down for me again?
Sure. So let me try to say it, David, and you tell me if I'm saying it correctly.
Yeah. Good.
So you burn a gallon of gas, and that gives off CO2. Everybody would understand that. And it's not, it's. By the way, David, do you know how much? I forget how much CO2 that is. Do you recall? In a gallon of gas, I should know that.
Not exactly.
But now that CO2 is in the atmosphere, and it has an impact, as we're talking about, for the next 500,000 years. Okay, so it's warming the Earth a tiny, tiny bit for 500,000 years. And by the way, most of the warming happens in the first 10 or 20,000 years or something like that. And we'll talk about that a little bit later. But still, it's over a very long time frame that this little extra warming is happening. So now you add up that warming over 500,000 years, you compress it to a single amount of energy, and that energy is equivalent to a Hiroshima atomic bomb. So but it's spread out over, incredibly long time frame. So it's very little warming in any 1 year, but it's cumulative.
So Thanos wasn't wrong, is the answer here.
What is Thanos?
That's a Marvel. Thanos, that's a Marvel movie thing. Thanos is the guy who, to save the world, he kills half the people. That's his theory. I
wouldn't recommend that, but
if I'm going to save the world. No. It's a Marvel movie, but hopefully somebody in the audience got that. But yeah, Thanos wasn't wrong. Honestly,
no. The point is,
break it down. It's like
No, there's a different
We're
answer.
all
The other
examples.
answer is to use energy that doesn't give off carbon. That's the right answer. Then you don't have to
But
kill
I
I
sort
stuff.
of
give off carbon.
yeah.
Yeah, yeah. So this is, but that's anyway.
Anyway, that's
if,
existential. Yeah.
so I think out of this room we're going to come out with that each gallon of gas you drive your car for each gallon. It's a Hiroshima atomic bomb. That'll stick with me. Okay. Well, speaking of, let's get to sort of near the end of your paper. You talk about what it would cost to clean up all of this carbon so that we don't have these impacts for the next 500,000 years. And you said it would be really expensive, and to me, it was kind of a bargain. Can you talk a little bit about what and I have your paragraph here if you need me to read it if you don't recall, but can you talk a little bit about what the cost is to clean this up?
Well, I'm not like a specialist on CO2 capture, technology, but I'm an admirer of David Keith, and he has this paper from a few years back where he has cost per ton of CO2. I think it's like $100 per ton of CO2
Correct.
is
Yeah.
what he calls an optimistic cost. I've also read a paper about maybe you can tell me if this is bogus or not, about using olivine. You mine this mineral and grind it up, and it will absorb CO2 spontaneously, and that could conceivably remove CO2 from the atmosphere for something like $10 a ton
Correct.
of CO2. So
right. Not been proven, but that's a project called Project Vesta, and that's on the low end, and I would say the high end at scale. We're not talking about today, but a gigaton scale, $100 which is what David Keith was saying, and that would be sort of the mechanical capture. And then there's sort of accelerated natural systems like olivine and others, and ocean phytoplankton and all these kind of things. All of those.
That's bullshit. Ocean phytoplankton stimulation is bullshit. That's a
good.
zombie idea that will never die.
Okay, well that's
Just
boy, we should have a room on that too. By the way, I know the person to bring in on the other side. We can have a big debate.
Oh, great!
But still, the bounds are like $10 a ton for accelerated natural systems to $100. But then you said at $100 a ton, the cost would be $160 trillion to eliminate.
That is to, yeah, right. So to get back to 350 ppm, which would eliminate that top of atmosphere energy imbalance.
Mm-hmm.
So it took like 440 gigatons of carbon in a model to withdrawn over 30 years to get the CO2 back to 350. And, you call it relatively cheap, but it's like 1.5 years of global world production. That's a big hole we're in.
Mm-hmm.
It seems like to me.
But 160 trillion is only 1.6 years of present day GWP. So to me, that sounded pretty good.
Yeah. Yeah, we just differ on the word only. Otherwise, we're in total agreement. Or you can also do it as how every year we're emitting more, CO2. How much would it cost to clean that up? And it's like a few percent of our GDP every year that we're kind of like living on credit if we're, ultimately going to have to clean it up.
Right.
So it's like somebody mailed us a credit card in the mail and we don't realize that we're going to have to pay it back. And
well, not us, but our children.
Percent of our income on it.
We're spending the money today and letting our children and grandchildren pay the bill, which some people think is immoral.
So it turns out that the cost of cleaning up the carbon is vastly less than the ultimate cost of carbon. But because the ultimate cost is not concentrated on any one generation, it may not be in any one generation's interest to actually clean up the carbon. So one point that was made by the reviewers is the maximum possible ultimate cost of carbon would be the cleanup cost, because if it cost more than that, we would just clean it up, and that would be like a limiter. But it's not clear to me that it would work that way because
it already doesn't work that way, because the cost of damage caused by the CO2 is orders of magnitude higher, even in the short run, than the cost of not emitting it, and yet we continue to emit it. So we've done that experiment already. People are not very good at looking at future damage and accounting for it. Would you agree?
So my co-author on the paper, Edwin Kite, calculated based on costs of building dikes in the Netherlands, how much it would cost to protect the whole coastline of the world with triple dikes, 120 meters high, and how big they are and everything. And if you divide that by the total amount of carbon that we would release to trigger all this sea level rise, it came to something like $5 a ton of carbon, which is so much smaller than the ultimate cost. But again, it's a problem with the timing. One generation may feel the need to take this on itself. So it's the economists were right. A cost that's unhinged in time like this is kind of really hard to do anything with. You can't do cost benefit analysis, really. You can't take it to the bank. It's just kind of a
well, then look at it the other way. It's also not proper to do a discount rate when it's not you who's paying the money back. It's one thing for me to take money and eat all the pizzas and then leave you nothing to eat, so you die of starvation. But I did the discount rate. It's only
right.
These pizza I'm eating, it doesn't affect you at all, according to this calculation. So, yeah, that's a whole other, it's almost a philosophical thing. I want to ask you some questions. I want to keep asking you questions here, and then also ask you about your Long Thaw book. But I'd like to open it up also for audience again. If you'd like questions of your own, please raise your hand. And I know Stacy has a question, so let's move to Stacy first, and then we'll get back to some of these other things.
Yeah, thanks, Dan. So I have two quickies, and one, I will apologize for being late. I am out of town and had something that ran into the beginning of this. And so you might have said this at the beginning, but I know people have joined us since you've started. Yeah. And that is, so all of this is based on the 500,000 year view. Have you done anything that is on a shorter scale, like a century or 1,000 years, or I don't know, something that we can more easily wrap our heads around? That's the first one. And then the other one is so I flew to the East Coast because we don't have trains, and how else am I going to get here? And so any ideas on what the cost of that would be, if we were actually pricing these things, or this isn't in your model, how to break it down for day-to-day travels. And I'm Stacy. Thanks.
So see, remind me your first question. Oh yeah, 100 or 1,000 year timescales. Well,
something actually, more manageable.
Yeah, one of the reviewers really was pushing for that, for more about, the short-term kind of details, and I didn't know how to do that because the way the model is formulated throughout this long period of time, it has these very unrealistic, assumptions about humanity in a steady state and living at the carrying capacity of the planet and stuff, which is kind of pie in the sky. And I didn't know how to, come up with a realistic transition to an unrealistic, thing. And, adding up the costs over the long time scales, what you would get from the first 100 or 1,000 years is negligible compared to, 100,000 years. It would be like 1% or 1/10 of a percent or something. So I did not know how to go that way. And, I did say at the beginning that I'm not an economist and I've never written anything about money before. And I probably won't again. I just sort of wanted to make this point. So let's see your second question, airplanes. Yeah, I was, there was a meeting in Washington about the social cost of carbon, and I could have flown there to give a talk about this, but I calculated that it would have cost, the ultimate cost would be like $40,000, and so I just did it over, did it remotely. I was into doing remote talks long before COVID happened. So right now, I'm actually in the state of Washington. Yeah, okay, I can't remember. Off the top,
a little less than half a ton.
Yeah, I did the numbers. Yeah, I remember it was a big. I don't remember offhand, but
well, I understand that flying in a plane is the same as driving. By the way, in terms of your your carbon footprint. But the thing is about flying is you're usually going very long distances. So if you drove your car to New York from San Francisco, it'd be 2,500 miles or so. That's a lot of gallons. And it's roughly the same number of gallons per person on a flight to New York from San Francisco, roughly speaking.
Yeah, it depends on how full the car and the plane and stuff is.
Exactly.
I was just going to say, that was from going from Chicago to New York, but I'm in Washington right now, and I got here by the train, which may be a factor of 2 lower intrinsically passenger CO2, per mile, but the train was running at half sort of capacity because of COVID, and I hear the airplanes. I haven't flown in 5 years or more.
The airplanes are full. I'll tell you that.
Yeah,
right now.
that's what I hear. So
Yeah.
I'm going back to Chicago on an airplane. I figure it's probably about as bad as the train was getting here because of the.
I don't know.
So I agree with you on it.
Plane's not lifted in the air. It's quite efficient actually. But you're right.
Well,
if it's half full, maybe
thing,
not. Yeah.
The other thing, because I've done these calculations too, my usual would be San Francisco to LA, and it's train, bus, driving, how many people are in it, how full it is. But the thing that is always the stopper is, unless it's a personal car, that thing is going to leave no matter if you're on it or not. So it's very difficult. Other than I'm buying into this and I'm further perpetuating that they should keep doing whatever that thing is. And the train, I'm in Atlanta, and that's just no contest. It's 3 days and at least 5 times the price, unless I did a coach seat, which would be pretty miserable for 3 days to get from San Francisco to Atlanta. That's just insanity. Who does that? So
not me. No, I rented the room too. And you're right, it's more expensive than flying.
And then we had Kevin Anderson on a couple weeks ago, and he hasn't flown, I think, in a way long time, 15 or 20 years or something. And he had a conference. He lives in the UK, and he had a conference in China, and he took the train. Took him 2 weeks, but he said it actually was quite efficient because he got a lot of work done on the train, number one, and he didn't just go there for a few days in China. He had all kinds of meetings over 2 weeks, and so it was a different kind of experience. So it's not always a bad thing. Anyway, but it would be really good to get rid of all this carbon. That's what we have to work on.
Edit. We need to edit that in. Don't tell Kevin that I flew.
Oh, all right. Okay. I'm sorry. I'll hide it from him.
It's the only way.
Hey, let's welcome John to the stage. And John, great to see you again. And what's your question for David?
Good to see you too. Thanks for having me. Stacy, I totally got the Thanos reference, and I think it's brilliant. It was very funny.
Thank you.
David, thanks for being here. My question is, how do we communicate this, in your opinion, to people? Because I've tried to talk to a couple of people after the shock that I had with the Kevin Anderson interview, and it just seems like really smart people are just completely indifferent to it.
Yeah, I don't know. If I knew the answer to your question, I would have changed the world. I've kind of gotten burned out on trying to argue to people that, they should care about this sort of thing. I don't know. Over the last years, it seems like we can't even agree on anything. So what do words even mean? So I don't know. I'm hoping that the Greta Thunbergs of the world can figure it out, because I'm kind of pooped.
Or we just need to Thanos this thing.
I hear you. Oh gosh, I hear you. And I haven't been at it. I've been at it a fraction of the time that you have. It's crazy.
Mm-hmm.
Well, I do think having this long-term view helps people understand a little bit, because our whole world is focused so short-term. And one example is sea level rise by 2100. We always stop there. Sea level rise continues for like 1,000 years. And even if we only hit, let's say, 3 to 6 feet of sea level rise, which is mind-boggling large number, by the way, for sea level rise, but by 2100, but let's say it's only 3. Oh, wow, it's only 3. But by the next century, it could be 15 feet. And if that was true, then the entire southern third of Florida would no longer be on the map. And yet we only look at numbers up to 2100, including warming, for that matter.
Right.
Yeah. So.
Right. Plus, the sea level will continue rising as the thermal expansion of the deep ocean and the melting of the big ice sheets, which have a long time constant, as we said. You won't be able, there isn't a stable level that you can, reference your building code to. The sea level is just going to be monotonically, rising throughout the rest of human experience, probably.
Hmm.
David, are you familiar with the Long Now Foundation? They might be good people for you to speak with.
Is
They're
that
focused
Danny
on like,
Hillis?
No, it's
Some kind of
I
10,000 year clock
yeah,
thing or
yeah, yeah,
something?
exactly.
yes,
Yeah.
exactly.
Yeah,
These
I've
are the
heard of that.
Here in
people.
San
Yeah,
Francisco.
and
Yeah.
they're based in
Mm.
San Francisco, and yeah, I love the work that they do.
Huh.
And anyway, you might have a good chat with them, and
Yeah,
they
you
do
would be a
like TED
perfect speaker
Talks
for them. That's
style things.
exactly
Yeah,
the kind of thing
Uh,
yeah.
they do.
huh.
And well,
There's also
speaking,
a thing in Bellingham, Washington called the Foundation for the Future that has had meetings on this kind of stuff.
okay. Well, speaking
Oh,
of that,
I yes, all that. Yes.
you wrote a book called The Long Thaw. So this is kind of
Yes.
staying on subject, but it's a little less on the economics, but just on the long-lasting implications of the things
Yeah.
we're doing today. Can you just talk about that book? What it's about, what some of the important points of the book are.
Well, it's, just making the same point about the longevity of the impacts. But so, like I said, I didn't discover this. It was first in this paper by Walker, like in 1987 or something, Jim Walker. And it was like figure 27 or something like that. So, I tried to send, papers to high profile journals, like Science and Nature and stuff to try to get, and well, it's already been published, so they didn't, want to see it again. Scientific American, um, it was like this established scientific fact that had made no penetration into the communal sort of worldview. So I wrote the book to try to, bring it out, and I think it's been effective. But that's why I did it.
So, well, let's still, again, some people might have just joined and things too, but let's just talk a little bit about the time frames then. So, we put CO2 into the atmosphere today, and from a geological point of view, it's like instantaneous. The last 100 years is essentially instantaneous, especially since like half of it came in
Right.
the last 30 years, which is just mind-boggling to think
Right.
about. So we do that, and then we start changes. And so, first of all, just how long does that CO2? I've heard, by the way, the number I've heard that CO2 lasts in the atmosphere for hundreds of thousands of years. But you're saying it's actually much longer than that, or is it just the impact it causes lasts longer? Can you explain that? Like, how about physically lasting in the atmosphere, a pulse of CO2?
Well, there's some confusion on this because if you track an individual CO2 molecule that gets released, it'll only be in the atmosphere for maybe a few years before it might exchange with another carbon in a plant or in the ocean or something. So the actual lifetime of a given CO2 molecule is shorter than the lifetime of the perturbation of having, more CO2s in the atmosphere than you would have if you hadn't released it. So that's kind of one point of confusion. Another is the best way to describe it to simply describe it mathematically is that there's like fractions of the CO2. So 50% of it goes away on an e-folding timescale of 1,000 years, say, or 300 years or something as it's dissolving in the ocean. So that takes you from all of it down to half of it or something like that. And then another, fraction of it goes away on a time scale, like another 25% or so on a time scale of thousands of years as you as the pH of the ocean and the buffer system of the ocean kind of recovers. And then there's like 10% or so that is the long tail that's left over after you've done all that other stuff. And that's the fraction that's going to last for, a really long time. So there's no way to sort of summarize the sum of like 3 exponentials with a single number and have it, come out right. If you actually ask what is like the average of those, it tosses out the long tail. So it's sort of, a question of, if you simplify it too much, you throw the baby out with the bathwater and you lose the long tail.
But while we're
But the
talking about
long
that,
tail is enough
go ahead.
to melt the ice sheets and do all this stuff that we're talking about. So, it's even though it's only 10% of what we release, it's still really important.
But actually,
And if we try to take out just that 10%, the biosphere would buffer it and put more back in. So, it doesn't mean that we can just clean up 10% either. We still have to clean up all of it, or, a big fraction.
But by the way, to be clear, when we put a ton of CO2 into the atmosphere, by coal plant or cars, whatever, my understanding is that relatively immediately, half of it goes away into the oceans, soils, and plants. I mean, so of the
That is not exactly true.
Okay, can you explain that, please?
Yeah, because CO2 has been accumulating in the system for a long time. So if we started in steady state with a CO2 that was stable and not rising and put a ton of CO2 in, half of it wouldn't go in the ocean in the next year. The reason why there's an uptake into the ocean this year equal to half of our emissions is because the atmospheric CO2 concentration is higher than the natural value because of all the emissions we've been doing in the past. So you're right about the numbers, that half is that we release is going in to the ocean every year, but it's not tied to how fast we're releasing it. It's tied to how much we released already.
So the first ton, the very first ton back in James Watt and his steam engine or whatever it was, that one did not get half absorbed? Is that what you're saying?
Not the year that it was released, no.
Oh, okay. So you're saying we put so much overpressure,
but some of it,
basically. We have
yes,
so much.
Exactly. Yes, some of that first ton is still in the atmosphere, and that's going in the ocean today. And it was not because we released it this year. It's because James Watt released it 200 years ago or whatever.
But when we release a ton today, is it correct to think that half of it gets absorbed by the way? Not, I think the oceans are about a third, and then the rest is soils and plants. But roughly 50 to 60% of the current emission is quickly absorbed by the biosphere. Is that correct to say?
Well, that's correct. Given how much we are emitting and how much has been emitted, in the past. But if we stopped emitting CO2 today, the amount that goes into the ocean next year would be almost the same as if we didn't stop, because it's being driven not by how much we release this year, but by the cumulative how much has been released in the entire industrial.
Well, I'm so glad to talk to you about
or
it.
if we were to suddenly release 10 times as much next year, the amount that goes into the ocean wouldn't go up by a factor of 10. It would be basically, the same, because it's not driven by current emissions. It's driven by the long-term history.
Well, that is super interesting, because I was trying to get my head around that, because I heard this thing. Actually, Jim Hansen told me about this, because I was talking about carbon capture. He said, by the way, if you do carbon capture, you have to do more than you think, because as soon as you capture a ton out, then the oceans will give back half right away.
Right. The oceans are buffering. Yes.
Yeah, the oceans are buffering. But recently, I came to understand what you're saying, which is, and this is sort of the good news, I guess, that if we brought our emissions down to zero, like 2050, let's say, we actually do it. We're at zero emissions in 2050. Atmospheric CO2 concentrations, which are currently 415 parts per million, and let's say by then, let's pick a number, 450 parts per million by the time we get to net zero, they would continue to drop, because the ocean will continue to. Now, this might be bad for the oceans, by the way, but for the atmosphere, the 450 would continue to drop, because the ocean has this inertia of capture, and you're basically saying that is correct.
Yes. Okay. But it won't drop all the way back to the pre-anthropogenic value.
No. But it would be better than the worst case, I guess.
But it does start to go down. Yeah.
So that's really important, by the way. But that's the good news. The bad news, let's see, if I understand, there's warming in the pipeline that we talked about earlier. This 500,000 Hiroshima atomic bombs going off every day. That's warming the Earth, and that would continue as well until the Earth is emitting as much as it's getting. So that's a plus sign. And I understand the continued ocean absorption of CO2 counters that to some degree, or it sort of cancels each other out, roughly speaking. I don't know if you looked at that.
So there's like I said earlier, there's this spike of CO2, and then the spike gets kind of smoothed out, the initial sort of spike. They sort of parallel each other, but the CO2 has a bigger excursion.
Okay. So, and then on the other side, on the plus side will make us warmer as we get to zero emissions. We'll remove aerosols from the atmosphere that are reflecting the sun, essentially coal smoke and things like that. And that would immediately warm the world. And then on the negative side, if we get down to zero emissions, we'll also get rid of methane and other short-term acting greenhouse gases, which would just basically, they don't disappear, they turn to CO2, but they're 1/3 of all the warming would go away. And that's countered by the increase of about 1/3 from the aerosols. And so that's why I think climate scientists are saying if we are able to get to zero emissions, like temperatures would stabilize. They wouldn't keep going up.
Well, Kevin Anderson made an interesting point the other day about nitrous oxide and methane, which are coming from agricultural practices that are not easy to, ameliorate. So there's warming from those gases that would continue.
Which is why why he was saying we need carbon capture, actually, just to offset that.
Yeah.
There's some emissions you can't get rid of. And I think people are being a little overly optimistic when they think about this net zero thing. But okay. By the way, have you looked into, there's this whole movement that says, gee, let me understand what we're trying to do. We're trying to get to net zero by 2050 using carbon reduction alone. At least some people are trying to do that. And if we're successful doing that, we'll end up with 2, or if we're not successful, 3 degrees of warming. And 2 degrees of warming would be an absolute catastrophe. So let me understand. The plan is to hope for an absolute catastrophe. That's sort of a simple way of putting it. So they say, hey, I got a better idea. Why don't we try to get back to 0 degrees warming? And let's use things like alveoline or carbon capture or other systems and it's called climate restoration. That's also, it's short. That's to address this long time scale that you're talking about. Have you looked at climate restoration at all?
It seems to me that we're rapidly shooting past where we want to be. So scrubbing CO2 out of the atmosphere is, my best hope for how things could work out. Then there's also geo-engineering in the sense of, solar radiation management, which, is kind of a horrifying idea on the surface of it. But again, I would recommend this Oliver Morton book to anybody who's interested. It really does make it seem like, well, things are already kind of unnatural on Earth anyway. We've doubled the nitrogen cycle by making fertilizers and, got all these parking lots everywhere and everything. So, but the thing about solar radiation management, either by putting aerosols in the stratosphere or, satellites at the Lagrange point to block sunlight or whatever, they all would take active, management and, continual sort of replenishment of the aerosols or something. So it's like we would, we would leave our children with this climate bill they would have to pay every year. So the only way to actually really fix it is to remove CO2 from the atmosphere.
Right. If you do solar radiation management without carbon capture, then you need to keep running the system essentially for thousands of years without ever stopping, and making sure nothing happens that stops you from sending those airplanes up and putting the stuff in the air or whatever. And I don't know how much confidence I would have of being able to do that. And then of course, if you forget to put the planes in the air for some reason, then you get all of that climate change all at once, and it would be, within weeks, and it would be devastating. So so do you think though that solar radiation management might be an important tool while we're ramping up the carbon capture, like to stop the Arctic from melting?
Well, so there's there's an issue that when you substitute, so what you're doing, you've got more CO2, so you've got more infrared light coming down, and so what you do is you put aerosols in the sky to get rid of visible light. So when you substitute from the natural world visible light for infrared light in the geoengineered greenhouse world, the infrared light doesn't promote water to evaporate in the same way. Visible light goes all the way to the ground and makes water evaporate. Infrared light gets absorbed by water vapor in the boundary layer of the atmosphere. So you have a dry, kind of arid world. Mount Pinatubo it gave a predictable cooling, and it was also kind of an arid climate for a year or so after that eruption.
Wow.
So you can there are papers about, finding the best balance between too much warming and too much drying. The paper about something called cocktail geoengineering, using different methods to try to, optimize things. But it would leave the problem of who gets to make the decision about, where to set the thermostat, which would, there'd be a lot of geopolitical conflict in that. And so a scenario that was spun in the Oliver Morton book is some virtuous country, I was picturing New Zealand, cleaned up its carbon footprint and then started to do this geoengineering and announced to everybody that they're doing it, and that any other country that managed to also cut their carbon footprint could join them in the governance of how to do it.
Mm-hmm.
He also mentioned the possibility that just some billionaire, we call this the green finger scenario.
Sure.
Goldfinger, but green finger, could easily, or some tin pot dictator, some little country. It'd be very logistically easy to do this. We wouldn't even know anyone was doing it if we didn't look at, who was buying weird amounts of sulfur or something. So I don't know. It kind of made the whole thing seem a lot less terrifying to me.
Okay.
And so it seems to me like that's where things have to go.
I tweeted out, and I don't know, David, if you have it in your bio, but you can find David's paper. I did tweet that out yesterday, so you can look for that tweet. My Twitter's on my bio, of course, and you can see the paper for yourself. And his book is called The Long Thaw. But David, is that still out and still available?
Yeah.
In, like Amazon and stuff like that?
Yeah. Yep.
So can you tell us?
University Press.
So before we finish up, can you tell us what you're working on now? What's your next area of research that you're focusing on?
I'm working on a paleoclimate carbon cycle kind of project. It turns out that past climate changes and what we can constrain about the carbon cycle things that drove them are a really important part of kind of ground truthing the climate forecast for the future. So one of the things that happens is you have these ocean plates, the plate tectonics, and in the ocean you're putting calcium carbonate sediment on these plates, and then they get subducted down to they reach the edge of where they're allowed to be at the surface, and then they get subducted down to the earth, and some of the calcium carbonate that's on those sediments will get recycled back to the atmosphere. So there have been models that kind of treat this in kind of a spatially unresolved way, just kind of stepping forward in time with like a box that you say is your sediments and how fast it gets subducted. But it hasn't ever been done in a way that kind of looks like a map of the real world. So I'm going to try to put carbon cycle onto a plate tectonics representation of the planet.
I always think of that the White Cliffs of Dover are the reason that we're here on Earth. That if it wasn't for CO2 being sequestered in formations like that we would be closer to Venus than we are to the Earth. So, wow. Okay.
There's a big imbalance today between how fast calcium carbonate is accumulating on the seafloor and how fast it's going down, the toilet in the subduction zones. And that's because all the subduction is in the Pacific, where the crust is really old and so it's dense, but all the calcium carbonate is in the Atlantic, because the calcium carbonate likes to be in shallower waters. So,
Is
the
that why
simplest
you
thing would
said
be
these
everything is in
ocean
steady
system,
state.
these geoengineering, like putting iron in the ocean to grow algae and have it die? You're saying that's why that doesn't work? Is that the reason?
No, that doesn't work because it's like 1,000-year exchange time for the ocean to control the atmospheric CO2. So the place where you'd want to fertilize the ocean to take up CO2 would be the Southern Ocean around Antarctica.
Mm-hmm.
And if you could do that for 500 or 1,000 years, you'd start to get somewhere. But if you just do it until the year 2100, the impact on atmospheric CO2 is pretty small, and the actual logistic problem, involved in trying to actually fertilize the Southern Ocean are just, almost hard to imagine being able to do that. So, I was able to do that much better in my model than could be done in the real world, and the impact on the CO2 in the atmosphere is just negligible.
Well, that's like a whole
Gigatones
other hour
or something.
discussion. So I'm going to turn to, we have another question. Chanakya,
Yeah.
please, welcome to the stage.
Hello.
Thank you, Dan, for having me. David, I have a quick question. Just curious if there is any effect of all the ocean pollution that is, and all the dumping that is happening in the ocean in terms of its ability to absorb carbon dioxide and the phytoplanktons to then create oxygen. Like, does it reduce it? Does it affect it anyway? I would love to learn.
I would like to know that too. Yeah, there's all kinds of impacts on, well, mostly on fisheries. I'm not so sure about impacts on phytoplankton. One thing that has impacted phytoplankton is the deposition of nitrogen in acid rain. So nitric acid might have caused kind of a regime shift from nitrogen limited to phosphorus limited in the Atlantic or something like that. But yeah, it's a wide open question, really. You have acidification of the water, and that makes it harder for critters that make shells out of calcium carbonate to grow. And then this calcium carbonate is important as what they call ballast to carry organic little pieces of dead plankton and plankton poop and stuff down, sink through the ocean down to the deep ocean. This is a crucial part of the carbon cycle called the biological pump. And so there's modeling studies and speculation about what happens if you change the biological pump. How would it change the CO2 in the atmosphere? But it's really hard to say with much with any confidence at all. And then another thing we know is that there was a big change in the atmospheric CO2 associated with the ice ages during the last glacial maximum. Somehow the orbit of the Earth tells the ice sheets in the northern hemisphere to get big, and then somehow those ice sheets, or that tells the CO2 in the atmosphere to go down, and that makes the whole Earth even colder. So it's a positive feedback that happened on those timescales. So right now, I mean, that was sort of like driven by temperature, causes a carbon feedback. Now we're driving carbon, but is there some possibility of a feedback from the ocean, as the temperature rises that could amplify the CO2? That's still an open question. But it would probably take place on a time scale of 1,000 years or longer. So it's not as immediate a question as, melting permafrost, for example.
By the way, speaking of that, the question I should have asked you, did you assume in a ton of CO2 that's emitted from, let's say, fossil fuel burning in your model, that gets amplified by permafrost release and other soil carbon release? Did you account for that in your model, or did you assume just the CO2 from the fossil fuel?
I did. It could be as high as 50% amplifier. So, like half, again, what we emit could come out of the by sort of feedbacks. Okay. If it was too much higher than 50%, then the whole system would be unstable. If you start a model with that kind of a feedback, a little blip will cause a little CO2 to go out, and that'll get amplified, and the whole thing will just sort of melt down spontaneously. So since the geologic record is not full of spikes of carbon, suddenly getting ejected in these warming events, presumably the feedback, is 50% or less. But we are starting from, a sort of cold position and a lot of frozen carbon in soils. So there is, a lot of room for feedback carbon.
Very good. Well, I want to thank you so much for your time today, and for everyone joined a little bit late. We're speaking with David Archer from the University of Chicago, and his paper on the ultimate cost of carbon shows that for every ton of carbon we emit today, the cost way into the future, if you add it all up, would be about $100,000 per ton of carbon, or is equivalent to $27,000 per ton of CO2. And we learned a lot. We learned a lot of interesting things along the way of that story, which I think makes that paper very interesting. It's not just about the cost; it's about how to think about
not at all.
Our long-term impact, which we're having on the world today. So, thank you so much for helping us understand that. And might have to have you back when I find the right kind of person who's pushing ocean sequestration. We can have a grand debate, which would be a lot of fun and I think educational as well.
Bring it.
Very good. So thank you, everyone. Thank you for coming. And again,
thanks, Dan.
Thank you, David.
Thanks, Dan, for everything that you do.
That concludes our interview with Professor David Archer of the University of Chicago and his research on the ultimate cost of carbon and the long-term impacts that CO2 has on our climate. To listen to other Climate Chat Club interviews, just search for Climate Chat Club on YouTube. Thank you for listening.